Okay, welcome everyone to the last day of VIScon. I'm Lukas. I will be the stage manager in this room for today. And we are starting with a talk by Christoph Bräunlich of BSI on how machine learning is making harbors safer.
Thank you very much. Hi everyone, and thank you so much for joining this talk. I have to apologize in advance for the title. It's not entirely correct. We're actually trying to make ports safer, not the harbors. This is a translation mistake. So just so you can, you know what you can expect from this talk. This is the description that we submitted, and it has two parts. First, how we developed our machine learning platform, and secondly, we'll focus on this specific use case with the ports. And specifically, it's the Port of Hamburg that we made a machine learning project with. When I was studying and I was listening to talks from people who were already working in industry, I always wanted to hear a lot of technical things. So I promised to show you some code. But let's start what our task was in the beginning. When we started with this machine learning platform, we already had an automation platform. It looks something like this. You can drag and drop these steps, these building blocks from the right to the center and connect them with each other. And it's sort of a visual programming language where you can automate all sorts of things. It can be marketing, events. It was also used for content management systems, so you can put websites in there, you can send emails with them, you can attach it to social media, but you can also have logic steps there. And the next step to even further develop this automation tool was to add machine learning features. And I was given, together with my team, I was given the task to develop that. And the task was a little bit more specific. We had already a huge variety of these steps, of these building blocks. My task was to extend it by 4 new steps. And I was already given a marketing term for this new module. It was called Brains. So we had this machine learning workflows called Brain, and there were 4 steps for this desired. One was just to execute an already trained machine learning model. One was to train it, to learn it. And then we had one step when it's not just enough to learn it with the workflow, with where it runs through. We also had a step to ask for review. If people know more about this specific case, can train the machine, then they can be asked with the 3rd step, review and training. And the last training step is for reinforcement learning. Okay, so when we started to build this machine learning framework, we had to look at already existing use cases that we did in machine learning before. One of the first machine learning examples that we worked with before we developed it was to further automate incoming communications of a company. So they had already static email rules that didn't work so well. So often there was a person that said, okay, this email rule didn't work quite as it should, and they had to reassign it to another team, and then they had to sometimes reassign it to another process, and they had to write the answer text by themselves. An example for this would be that an email comes in, I want to change my address, and then the email rules should automatically figure out that the process to change addresses, to change customer data should be ran. So our task was to exchange these email rules by a machine learning engine that is running it automatically. And it also had to choose the process, not just the team, and it also should propose a text to answer this email for the end customer. What we did at that time we didn't have transformer models yet. We had to use things like an algorithm called doc2vec, was an algorithm from Google at that time, to classify each part of the emails, put it into a fully connected neural network, and then it was for this German company figuring out what processes to start. And now the task again was to implement this into BSI Studio, this automation platform that we built beforehand. Another example was for the Swiss Post. And the Swiss Post at that time was building a payment slip vending machine where you can just put your payment slips onto the machine. It was scanned and it should recognize the handwritten letters by itself and the addresses and so on. So what we did there, what we did there was we had this scan. We already had it in a digital form from the scanner, and we had to figure out the specific parts of it. And we did that by first finding the correct positions of each letter or number. We used the framework, the OCR framework Tesseract for that, because it was already did most of the work. Then we cut out the single numbers, changed it to grayscale, and then used a method called OTSU, which is transforming the grayscale image to a just entirely black and white image. And to make it easier for the neural network to figure out what the number or letter is, we centered the number by calculating center of gravity and then moving it. We resized it to 24 by 24 pixels, so all the numbers are exactly the same size. Then converted it into a decimal matrix and used the neural network for classification. And this neural network architecture is already a very old one. LeNet 5 was the first one that was used convolutional neural networks for this. But for this task, it was very fast to train and worked perfectly. So if we have a look at that as a workflow, it looks like that, all these steps that I decided, and at the end, it figures out what numbers or letters should be used. So with these two use cases in mind, we went and tried to design how this new framework, this brain, should look like. First, we wanted to have a visual representation of that. Visual representation for us is important because we wanted to have this as a platform where technical people can interact with maybe people in marketing or people in sales. This communication is always a huge problem in the business world because the data scientists, the machine learning engineers, they usually use Python and R for their models, and nobody else understands how this works. And when you give it to a marketing person, he doesn't know exactly how to implement it in their workflows because they don't know what's behind it. So we wanted at least a visual representation that these two people can talk with each other. And this was our idea. So we had different data types for it. We have also building blocks similar to what we did before in the automation platform Studio. And we have an interface to Studio. The interface is inputs on the left-hand side and outputs on the right-hand side. And with these inputs and outputs, we can connect it inside. So we went to a graphics designer and asked him, can you make this beautiful? And that's what he did. He said, okay, let's keep it simple. Let's not make two lanes on the left and right side. Just make inputs and outputs. And then put these building blocks in the middle. And we again had to come up with some marketing terms for this because we also need to sell it. So these building blocks are part of a brain, and we called it Cortex, like the visual cortex, or so on. And then we implemented it, and we again made some changes with it. It looks like this now. So on the left-hand side, you see an input. The brown ones are the outputs. We changed the colors so that these are the same colors that we already used in Studio, but otherwise we didn't make a lot of changes. And here you also see the window open where you can edit a neural network, and this one is exactly the LeNet that we had in the example before. So this one is doing a very similar task that you saw for the Swiss Post. You see all these building blocks where it resizes and centers the image and then puts it into a matrix and finally puts it to the neural network, and we have the outputs possible here. Another problem you usually have in the business world is to manage your models, your trained models. And if you, for instance, think about the weather prediction, you might have the same structure of a brain for several locations. If you want to make the weather prediction for Zurich and also weather prediction for the hill close to Zurich currently, then you need two models, but you have exactly the same structure of a brain. So we came up with the concept of mindsets. Again, a marketing term. I'm sorry for all these marketing terms, but it makes it easier to have a language where you can with each other. So you can train the brain several times and always create a new model with different data, and you come up with a mindset. And here is another example of how this looks. This one is, by the way, a very simple weather prediction brain that we used for teaching engineers and marketeers to use this tool. But now I want to go a little bit behind the scenes and get a little bit more technical. When we look at this brain, we have different kinds of cortexes. We have some that need supervised learning, some that just need to be executable. They're static, they just calculate something and put it out. And we have some that we call unsupervised learning. They just need input data. They don't need a target where they can learn to. And these graphs that we draw, they're go into the category of unsupervised cortexes because they need all the data series. They don't need a single sample, but they need the whole data set. And so the interesting part now is how does all this data flow together? So we have blue incoming data and brown outgoing data, and we also use this outgoing data for the target data. When we want to train a brain, we fill all the inputs and the outputs with each sample and run it together. And it looks like this. What we first look is for all the supervised cortexes, and we prepare all data for this. So we move all data from all inputs that are required for this cortex, backpropagate all the data from the outputs to this cortex, and then run it. Next part would be that we go through all unsupervised cortexes, calculate all the data that needs to be there to use it. Now we can execute the supervised cortex because it's already trained. And we continue this. Here we don't need to execute any data anymore because we already have it in our graph. And go to the last one, and then we can execute the unsupervised as well. And we finally have our output data, and from now on we can use this data just by inserting input data, and the output data will be calculated, and we can integrate it into our automation platform. I want to dive a little bit deeper. I will, in this talk, I will go deeper and deeper and deeper until you see the actual code. So, but first, some considerations for the architecture. This is was our state, our architecture of the applications that we had so far. We had a CRM software, we had this automation software called Studio, and they have very different requirements. The CRM only needs to be available during office hours because it's only used in the office. But the Studio, I told before that it has landing pages inside websites that it needs to host, it has emails that it has to send, SMS and social media and so on. It needs to react 24 hours a day for this. It needs to be highly available. And so we asked ourselves, how does the machine learning platform fit into this landscape? And the first thoughts were, okay, we need different hardware, so it should run on a different set of computers. We usually need graphic cards for our deep learning models. And one decision was to make it stateless. So we want to be able to make it scalable. We want to have as many of these machine learning engines as we want, and we want to be able to distribute all the executions to all of them. And if we have a database there, we have the additional problem of distributing all the data, make a huge, complicated distributed systems. And by just using the database of Studio for it, we were able to simplify it and to just have the data at one place, send it to the machine learning engine when it needs to be calculated, and sending also the samples there when we need to execute them. Another very important part for us was we want to make this platform extensible. We want to be able to run it in a very different way for all our customers. We have a huge variety of different customers that use it differently, so we need to be able to make it as extensible as possible. And the first thought was, of course, to make these cortexes extensible, make it possible that we can add as many cortexes as we want as easily as possible there. So this API for the Cortex was very important for us to be very easy. So the general ideas, what we needed to have for a Cortex was, of course, a UI where we can click on. You saw this UI for the neural network Cortex before, and the logic behind. These are the yellow blocks. And then we need to have a state. The state are the blue blocks. The state consists of a configuration. We have it in JSON format. It consists of logs. We want to be able to see what's going on there, what's going wrong. Then we want to have statistics. When we want to train a neural network, we want to see the learning curve. We want to see maybe if it's a classification problem, a ROC curve and confusion matrix and so on. And if you paint the graph is the statistics. And when we train a model, we want to save the model, usually in binary format. The input and output that we want to have at least one method, and for maximum 3 methods that you need to implement inside of this Cortex. The easiest one is the execute. When you get input data and you want to calculate the output data, you just implement the execute method. Some cortexes need to be backpropagatable. Then you need the reverse operation in a second method. And then there is the third method, the train method, that gets an iterator over all input and output samples, and you can stream it through there. And again, it was important for us to make this part stateless, so we can send this part to all our different machine learning engines and just replicate the blue blocks in the state. So I promised to go into the code, and what I will show first is what we will implement in the code. We have in this Cortex 2 parts that we need to write. The general part is already implemented. You just implement an interface, and the right-hand side is already there. So we are putting a special interest into this specific part. In this specific part, you can tell how to visualize the statistics. You can see the logs. And you have a low-level editor where you see the JSON and you can alter it there, and it will also be automatically synced with the UI. And this configuration, that's the code for the configuration. We need to have it because the UI is written in JavaScript and the backend is written in Java. We need to have an interface through it. So we have this JSON format, and it can be automatically by our framework be transformed into a class, into a bean that we can send it. And this bean, we just need to define our properties, and the rest of the code, the boilerplate code, is generated automatically. And there is one important aspect for us. This software is only successful if it can evolve, if it can get better over time and can change over time. So a migration was very important for us. You see this annotation on the top. These ML type versions 1, 2, 0 means it's this version, and if I see a higher version, I need to transform it into the newer version first. Okay, and now let's have a look at the source code for the UI. UI is written in JavaScript, as I told, and it would be maybe not so wise to place all widgets and create classes for widgets and place them at the right position. Maybe you want to have a more verbose language to do that, more verbose structure to do it. And so we also use in this JavaScript just to place the different components, we use the JSON. Just the UI logic is written in JavaScript, and you can very easily implement for instance, if you want to sync, just simply sync the fields that you have in this UI with the configuration. You can just put it to this map on the top, and this map will do the rest for you and write it down into this JSON configuration format that we have. And for me, the most interesting part, of course, is the logic. And we wanted to have this logic as easy as possible to write. On the top, you just see that you need to write an ID. This is just a simple plain UUID. You can generate it with online tools. We made an extension for our IDE that we can just write UUID and press enter, and we have a new one so that each Cortex has a unique identifier. And then we have metadata, where we place it on the right side, what color it has, what icon it has, what's the name, description, and so on, and in which categories we'll find it. So also very simple data with a very simple builder design pattern that we used. The next step would be to make a default configuration. This Cortex here, the logic of this is to resize an image. So by default, it will resize the image to 32 by 32 pixels. And at the bottom, you see the execute method. And as you can see, it's very, very easy to implement that. You just get an input. As an input, you get an image. We have our own type system, so we call it ML image because we want to be able to stream all this data. It needs to be fast. And we have the state. The state all sits in this Cortex mindset. And we first load the configuration by how many pixels we want to resize it. The second line is how we resize it, actually. And the third line is to generate the new image that we have. One question that you might ask is, so how did you do the deep learning stuff, all the neural networks and so on? Neural networks are changing all the time. There is research done almost every day, and there's a new paper coming out almost every day. So we need to be very fast there, and we don't have the manpower yet to handle this by ourselves. So we used an open source framework called Deep Learning for J. We had a lot of contact with them beforehand, before we even started. We did projects before, and our open source software is also in the Eclipse Foundation, so we persuaded them to also join the Eclipse Foundation because they had a little bit an issue with code quality, and if you go to a foundation like Apache or Eclipse or so on, they will really help you to make it better. And we have our own format that is independent of Deep Learning for J. It's also in this JSON format, but we can very easily transform it into a Deep Learning for J model and run it on their platform. But if we at one point want to change the backend to maybe TensorFlow, PyTorch, or something like this, we can just write a mapper that maps it instead of to Deep Learning for J to another framework. In case you're wondering, this is the code that does the mapping so far. What you can see here is that we have these generators that you can use and register, and then they will, this you can just replace, and then you will be able to put it into another format. And Deep Learning for J, of course, is not the only thing that we used in our Cortexes. We have many other things. We used, for instance, OpenCV to cut out faces of images. We have genetics for genetic algorithms or genetic programming. We use Apache Spark for simpler algorithms, and we also have scrapers and web scrapers built in. For this, we use JSoup, and of course, we also implemented a few algorithms by ourselves, by BSI. Okay, let's go to the second part and see what we did with this framework. What was one of our first tasks with it? And this is a task. This task was to do predictive maintenance at the port of Hamburg. And specifically, we had to predict how long the hoist ropes of this harbor train, how long it lasts. And for us, there are three types of ropes in these cranes. The hoist rope is the one that does the heavy duty. It's the most important one. If this breaks, the containers just fall down. They're boom hoist ropes. They're just static. That's why they're not so critical. They don't move. And the trolley rope is just moving this little cabin where people sit inside around. It's also not very critical. So for us, the most important part was to predict how long the host rope lasts. And this is, by the way, one of the biggest costs for the port of Hamburg, besides salaries. They already check the ropes regularly, every 3 months. They check whether they have any cracks inside or the diameter changes. And if they don't comply with standards anymore, the standards are given by the constructors of the ropes, they have to be replaced. And if you cannot predict very precisely when you need to replace them, you have to order ropes anyway in advance, because these ropes are coming from Austria and Switzerland, the same ones that used for cable cars. So you need to order them in advance, and not a few times they came too early and the other ropes were still in place and they were even starting to get rusty on the port. So what exactly is the problem? If we test too often, it's very expensive to go there. You have to do it manually, you have to move it a little bit, because exactly these parts that are moving, that are being turned, they're the most critical ones. And to get access to them, you need to disassemble some parts and go there, put people there in harnesses and so on. And if you don't use it, test it often enough, they could break before because you don't realize it. So we needed to find this sweet spot. And we also got requirements from the Port Authority. The requirement was to figure out, with the precision of 350 hours, when it will break. And this 350 hours this is about 2 weeks, and we only needed to be correct in 75% of the cases. Before we did our project, they were able to predict it with some mathematical formulas. They were able to predict it to 2 months, the precision of 2 months. So what was the input and the output of our brains? We used these continuous measurements, the electrical induction, and we used also these regular checks on these heavily used sections, and the accumulated weight that was handled with this crane, and then also what is of course important, in what seasons they run. And the output would be the remaining hours, how long this rope still lasts. And the brain that we did looks like this. We used 2.5 days to create this brain. So you can see how fast such a process works. And these 2.5 days, they were not time that data scientists use for it or machine learning engineers. This was mostly meetings that we understood the problem exactly how it works. So we configured the brain, trained it with the data. They already collected the data before, so it was in a very nice format with very good data quality. You don't see this very often in industry. We analyzed the results, and then we repeated all the steps and improved the brain. So let's look into the brain more precisely, what we have here. First, let's have a look at the neural network that we used. We used a neural network. Maybe not all data scientists would agree with us, but this was the first Cortex that we implemented, and we had it already, and it worked quite well. And it was a very, very simple one, just 3 fully connected layers. And you see they're very small. They have just, this first layer has 32 nodes. So it's a very small network, but for very little data, this is quite sufficient. And it's quite sufficient because we used a trick. We used a trick that we scaled the features and the targets that came in. So the target values and the features we transformed before we put it into the neural network. I will explain you why. So we used, by the way, a logarithm transformation. And on this graph, you can see precisely why. What do you usually do when you have a model? You make a residual analysis with it. Residuals are the differences between the expected output value and the calculated output value. So you see the measurements that were done in orange and the predictions in blue, and the difference is red. And on the left side, you see that they're not in the middle always. And if you transform it with a logarithm, they go here and they're always much, much closer to the center in average. And this is a big help for neural networks. If you transform the data into this, you can improve the model by a lot. So our solution then was correct not just in 75% of the cases, but in 93% of the cases in this 2-week interval. And it was improved by 2 months. So thank you very much for listening to my presentation. If you're more interested into more complex cases that we did, we'll have a meetup. You can just scan this QR code and join us at this meetup, and I would be very happy to see you there. Okay, if there are any questions, I will be happy to answer them.
Okay, so if there are no questions, then let's thank the speaker.
Thank you very much. Wow, that's nice. Thank you for listening.